So we've gone through, we did all the biaxial stuff, then we went into pressure vessels and then torsion, and now we're going to start looking at beams a bit. So what we're looking at is when we load up a beam, there's a simply supported beam shown there with a force on it. What it does is it bends, okay? And we quite often want to minimize the bending. The more extreme the bending, the higher the stress in the beam and that sort of thing. And we want to reduce that, generally speaking. All right, now the beam actually bends about a certain line. It's called the neutral axis. And the neutral axis runs down the length of the beam kind of like that, okay? Now, what happens when a beam bends is it changes shape a bit. It starts off as a rectangle, and then when the load's applied, it'll bend into some other shape that isn't a rectangle. So the beam would start like that. And then when the load's applied, it'll change its shape. Of course, a normal beam wouldn't do quite the extreme bending that you're seeing here, but that's the idea. It's not a rectangle anymore. And what it does is it stretches on the bottom and compresses on the top, okay? So what I have there obviously is a phone book, but that serves as a model that'll serve the purposes I just want to go over here for a beam. What happens here, if you think of those pages in the phone book as being sheets of atoms in the beam, is what the sheets of atoms want to do is slide across each other and go into this format right here, this shape right there, if you bend something. Okay, the outer radius over here becomes longer because what's happening is you're taking that rectangle and you're turning it into a section of a circle basically when it bends, or maybe not a circle but some sort of curve. That outer radius gets longer and the inner radius gets shorter, okay, as this thing tries to turn into a sector of a circle, okay? And when that happens, what the atoms want to do, and the pages in this book, the inner radius wants to slide out and the outer radius pulls in a little bit, okay? That's what happens. However, there's atomic bonds there between the sheets of atoms that don't allow that to happen. So basically what has to occur here is the right angle on the rectangle has to hold. If that doesn't hold, you're getting failure. The atoms are starting to slide one across the other and the beam's starting to break, okay? So you can't have that, all right? So what the beam does is it holds itself together. And so that puts stress and strain on these atoms here. So this side has to get pushed in and this side has to pull out to hold that right angle, okay? So the bottom of the beam stretches and it's in tension, and the top of the beam, in this case, has to push in, and that's compression. Okay? So that's the deal. Right? Now there's a line there. So what you have on the beam is the bottom part of the beam is in tension, it's stretching. The top of the beam is in compression, it's being pushed in. There's a line that runs right down the middle, and that's called the neutral axis, and it's called the neutral axis because it's in neither tension or compression. It's the boundary between the two. Okay? So the first thing we'll start looking at here on designing a beam is finding the neutral axis. Now the neutral axis runs down the length of the beam, like that. It's down, but where it runs through is the centroid of the cross-section of the beam. So what you want to do first when you start designing a beam is figure out from its shape where the centroid is on the cross-section so you can identify that neutral axis. It actually runs the length of the beam, is what it does. Okay. So that's step number one, is to find the centroid of the beam. So we good with all that? We got any questions on any of that, what I'm talking about? So centroids are on page 700. So let's have a look. Now the word centroid comes from the word center. It means in the middle. If you have like a plate, the centroid is the balance point of the beam, okay? Or of a plate, that's how I think about it. It's the middle of something. Now the middle is quite easy to identify if you've got a small or a symmetrical shape. If you don't, you've got to do a little bit more work to figure out where the middle is, okay? So down below there with those sketches, you see the idea of that neutral axis and the centroid on the cross-section of the beam. Okay. So what we need to do here to start to figuring out this bending reactions of the beam is to figure out where the centroid is in the cross-section of the beam. And the formula that we went over in statics, you know, if you had statics, which you should have if you're here, is it's basically a weighted average, okay? So what you do is to find x bar, you break the object up into pieces, you find the centroid to each one of the pieces, you multiply that by the area of each piece, then you divide it by the total area. Okay, so this is the general formula. Now if you've got a shape made of triangles and rectangles, which quite often we do with our beams, or we can at least approximate them that way, we can just use these standard formulas for centroids, you know, and they're easy enough. For a rectangle, a centroid's in the middle. So you just go over the base over 2, and you come up the height over 2, okay? And that's how you find the centroid of a rectangle. Right triangle is a little different. With a right triangle, the centroid is what I'd call the third point. I don't know if anyone else calls it that, but that's what I call it, because it's a third of the base and a third of the height for a right triangle. Okay, so that's how you can locate the centroid of those simple figures. And that's on the back of your formula sheet on the right side, about 2/3 of the way down. Okay. Now, if you can't break the shape up into simple triangles and rectangles and shapes like that, sometimes, and if you have functional relationships, you might have to add up by integrating. So then that would become dA over A, and then y bar would be the integral of y bar dA over A, like that, okay? So you might need to do that. Generally speaking, for standard structural work, rectangles work pretty well, you know, if you're looking at different types of structural shapes. So let's look at one of these. So, you know, I always like to get my information as organized as I can, so I just make a table for doing these. I make a column for the area, a column for the either x bar or y bar distance, and then a column for y bar A or x bar A. Then I just have a rows for the different parts, and then a row to sum everything up. So if I have a shape like you're seeing there, which is just basically a 5x4 rectangle with a 1-inch triangle on the top, I would break it up into 2 pieces. And so you could do this a couple different ways. I would break it up like so. There you go. So I've got A, which is a 5x4 rectangle on the top, and B, which is a 1x4 triangle on the top, or excuse me, a 5x4 rectangle on the bottom, and then a 1x4 triangle on the top. Call those A and B. And then, you know, off you go. You just calculate everything. Usually I put the units on the top. That way I don't have to write them in all the time. So what? A is 5x4, which is 20. And B is a triangle, so I need that 1/2 in there, 1x4, so that's 2. So the total is 22 centimeters squared. Now for y bar, what I want to do is measure up to the centroids. Okay, so I'll mark those. So the centroids are here and here. 1/2 of 5 would be 2.5, right? And then this one would be what? 5 plus 1/3. Okay, so that would be 5.33. Okay, so for A, the total height is 5, so 1/2 of that is 2.5. And for B there, what I'm doing, I'm taking the height of 5. Now I have to measure these from a standard reference. Once you pick your reference line, you got to stick with it throughout the entire calculation. typically you use one extreme side of the object or the other. I'm using the bottom here and I'm measuring up. So what I would do there is I would take 5 to get to the top of A, and then I've got another height for the triangle of 1, but I need the centroid, so it'd be 1/3 of 1, which would be 1/3. So that'd be 5.33. Okay. And then I would just multiply them together to get the y bar A. Okay. So that's how I do this. And I like to set up a table, and I like to draw pictures. Okay. Just to improve my accuracy and to not make errors there. So I got 20 times 2.5 is 50. 2, which is the area of B, times 5.33, 10.67. I get 60.67 for the total y bar A. Divide it by the 22 area, and I get 2.76, basically. Okay. So that's the process there. And I'm just doing that, I'm taking that into 2 shapes and just working through the area and centroidal distance for each shape, and then adding the results together. Now, of course, you can do this by subtraction also if you want. So why don't you guys do one of those? So let's do the same shape. So basically we'll take this as piece number 1, and then we'll cut out the triangle. So that'll be a cutout. So we'll call that 1 and 2, Roman numeral 1 and Roman numeral 2. So why don't you go ahead and do the bit for 1. What's the area, what's the y bar distance, and what's the product of the 2? Yeah, it's the same shape. We're just doing it in a different method. So 4 by 6 for the full rectangle there, I think. Or is it? It's 4 by 6. Yeah, 4 by 6. Doing all right on that? 4 by 6 would be 24. Half of 6 is 3. 24 times 3 is 72 for the first one. Is that good? How about the triangle? What's the deal with that? Yeah, very importantly, it's got to be negative because it's a cutout. See, it's the same area as the other one, but it's negative. So we get 24 minus 2. See, this bottom row is going to be the same. It's 22. How about y bar? What do you get for y bar for that cutout triangle? Yeah, it's 6 minus. And then what's going on here is it's a third of the distance. Well, there's two different ways to do it, I guess. The first way is to say, if I start at the top, I'd go 6 minus a third. If I start at the bottom, I'd go up to here, which would be 5. And then, being as I'm coming from the vertex side, it would be 2/3, okay? So that's 2/3, and that's 1/3. So it's 6 minus a third, or it's 5 plus 2/3, okay? And either way, you should get 5.67. So just pay a little bit of attention on those triangles. I mean, rectangles are symmetrical. This side you start on, you're going to get the same sort of thing. But the triangles, you got to watch. And, if you're coming from the right angle side, it's a third. But if you're coming from the vertex side, the acute vertex, or I don't know what the heck you want to call it, but it's 2/3. Okay, so just remember that. Okay. And then remember the negatives also. Okay. So the bottom comes out to be the same thing. It's 60.67 over 22. Same y bar, of course. Okay. So, and then the other thing is, remember to add in what I call the offsets. You're always coming from some reference line. I would tend to use the bottom of the shape for this one, and then measuring up from there. So you have to, you can't, like on that triangle, I've seen people make an error where they say the y bar distance on the cutout would be 2/3. Well, it's not 2/3, it's 2/3 plus 5 more, because you got to add that 5 in there, the offset from to get up to the base of the triangle, or to the vertex of the triangle, as the case may be. So we doing all right with that? Okay, so that's just how you calculate a centroid there. All right. Now, that's step 1, and the purpose in doing that is to find the neutral axis. Okay. Now, what we really want to do with this, or one of the things we do with it, actually do a couple of things of this with beam design, but we want to find the moment of inertia of a shape. And that's done about the neutral axis. Okay? So the moment of inertia of a shape, we'll talk about what this is, but we calculate it about the neutral axis of the shape. So again, this gets back to the bending of a beam when it's loaded, and the kind of that flexed shape. All right, so I'm on page 710. So I'm going to ask you some questions that might be fairly obvious. Now, the beams under your floor are called joists, okay? They used to be 2-bys. Now they're a little fancier, but back in the, to the 80s probably, they used 2-bys to build your floor in your house. So which floor joist would have the least bending, do you suppose, for that load we're putting on it? One on the top or the bottom? We would hope the bottom, because it's bigger, right? Okay, so now the reason we're going through this is the moment of inertia is a number that tells us how a shape will resist this bending action, okay? So the first thing I'm finding here is the bigger the beam, which would translate to my mathematics as being the bigger the area, the higher the moment of inertia, okay? The bigger the beam, the less the bending, okay? Which also means the bigger the area of the cross-section of the beam, the higher the moment of inertia. Okay? But it's more than just shape, it's also orientation. Those floor joists are the same area. And which ones would have the least bending there? Yeah, top one, right? It's more than just how big the beams are, it's how you orient them. And obviously you put the long dimension of the beam vertically to resist, to hold, to support the floor, okay? So you have to account for both things in the calculation for moment of inertia, okay? So the two factors are area and offset distance. My hand's about as big as the screen, so it gets me into trouble sometimes. I'm always hitting buttons and doing things. There we go. Offset distance, okay? So those are the two things. So if you look at the basic definition of moment of inertia, now this is an area moment of inertia, and I want to call that out. You did this in statics. In dynamics and physics, you very likely use what's called a mass moment of inertia, which is related, but it's different. This is based on area. Mass moment of inertia is based on the mass of an object. So this formula here for moment of inertia is the integral sign means to add up. Okay, that's what that means. Then you're going to break the shape into a bunch of little areas, which I'm calling dA. And then you square the distance from the axis to the area and multiply that by the area. And you keep doing that until you've covered the whole shape and you add everything up. All right, now the units for moment of inertia are kind of funny. They're length to the 4. Inches to the 4, meters to the 4, millimeters to the 4, whatever, because you're taking the square of a distance times an area. So you get meters times meters for the square of the distance, then meters squared for the area. So you get a length of the 4 for the units. Okay. All right, so we went over this a bit, how a beam will bend about its neutral axis. And the idea, if it sags downward or bends downward, we got tension on the bottom, compression on the top. All right, so what we want to do is minimize this typically. So what we want to do is have a high moment of inertia while using a small amount of material. Because what material does is it adds weight to the structure and it adds cost. So you want to get the biggest moment of inertia you can get for the smallest amount of material. All right, because here's our formula right there. We want to keep the dA as small, or the total of dA as small as possible. Again, because higher area means more weight, more cost. So what types of shapes do you typically use in structures that have a high moment of inertia while reducing the amount of material? What do we make stuff out of for structures? What shape, typically? Yeah, I-beams, yeah, right, okay. So what you're doing with an I-beam is if here's the neutral axis, which goes to the centroid, is you're trying to get the area a long ways away from the axis, okay? That's what you're attempting to do. Those are the flanges. You want the flanges set out away from the neutral axis. Now, as best you can, now obviously you can't have an I-beam for a house that's 4 feet, deep, and that's ridiculous, right? You can't, so you have to keep it within the constraints what you're trying to build, but that's the basic idea of an I-beam, okay? Now, there's different kinds of I-beams. Okay. Here's the original ones were called American Standard. I think these were used around the turn of the century, the old century, I guess 1900, around then. I think maybe the Empire State Building in New York is built out of standards, okay? But they have a weakness. Okay, now what they are, they're narrower, and they have what we call a fillet, a rounded edge on them, like that. Now they've got a little bit of a weakness. See, they're fine for that kind of load if you push down on the beam. Now keep in mind, what's happening here. The beam itself would extend into the page, so the beam is doing something like that, okay? Oh boy, this isn't going well. It's getting a little bit off center, but yeah, I was doing okay. But You know, it's funny, you don't have to be an artist to draw, you know. It just follows these kind of mathematical rules. They're just kind of projections, what they are. So it's a difference between drafting and drawing, maybe, I don't know. That's kind of weird looking, isn't it? Okay. All right, so we got something like that. Yeah, okay. So American standards work fine in a vertical load, but the problem is when you start loading them from the side, they're weak, okay? They don't handle that very well. Now, why would I care about sideways loads if I'm making a building or something? Yeah, earthquakes, yeah, lateral loads, okay? So, especially in this part of the country, we care a lot about that, okay? So, what they've evolved to now, most beams are now a wide flange. They're squared, they're a little stronger flanges, and they're wider. They resist what I call lateral side loads better, okay? Now, we also have some other ones. We have heavy pile, which is used if you're like building a foundation. One way to do it is just pound these things into the ground, kind of like you drive a nail into a board. If you run around one of these jobs, you'll get a headache after a while because they just have this big heavy weight. They lift it up with a crane and they just hit it like a nail, and they hammer on a nail and just drive it in. Now, it has to be really strong to resist those loadings, so they make them quite thick. And then there's also a category of beam that isn't any of the above, so that's the miscellaneous category. Kind of picks up some miscellaneous ones. Usually they're kind of halfway between a wide flange and an American standard, I think. I'm not entirely sure of that, but I think that's kind of the deal. Okay, then you can take standard eyes and cut them in half. If you cut them across this way, you get T's. If you cut them down the length of the web there, you get channels, okay? Now, columns, you want them to be strong in all directions because columns can be loaded in any direction. So the common things there are pipe, and they actually use like pipe, you know, there's different types, but they use schedule pipe, you know, like a plumber type designation on that. They also use other types of pipe, and they make tubing, which you take a plate, you just bend it into usually a square. A nice little trick on columns is you put the column in there that's the metal pipe or tube and fill it up with concrete to stiffen it up. Okay. So there's a few structural applications there. There's a column that's made out of an I-beam. Here's another I-beam itself right there. Here's a double T-beam made out of precast concrete. That's what we used a lot on this campus here. That's what the roofs are made out of. Either that or these kind of waffle kind of patterns that you might see. Here's a column made out of a tube. Okay. There's a square concrete column right there. So there's kind of the standard shapes, you know, as they're used. Okay, now in the old days for houses, they just used 2x for floor joists. 2x8s and 10s, I think, primarily 2x8s a lot, I think. I'm not sure, but I think it was 2x8s. But nowadays you use this TJI. They're cheaper to make, they're lighter. They're kind of this press board for the web, and then they have these small flanges. And it's just cheaper and lighter. Okay, now I-shaped beams are, you know, very common. There's a standard call out for these that you should know. The shape letter comes first. Then what's we call the nominal depth. Now the nominal depth means not an exact depth, but a depth that's used as a category, okay? So W would be the shape, that means wide flange. 36 means about 36 inches deep. It might be 35 and a half, it might be 36.4, something like that. It's in the ballpark of 36 is what that means. And then because we care about loading, we call out weight per foot. So that would be 300 pounds per foot. So that's a W, shape is a W, nominal depth is 36, and the weight per foot is 300 pounds per foot, because that goes into the load calculations. So that's how you call out an I-beam. The horizontal pieces are flanges. They're joined together by a web from outer flange to outer flange. It's called the depth. Okay. So we all right with that?
What are the next term, the nominal depth?
The nominal depth, if you look on a table of I-beams, what you'll see is they're not exactly the first number in depth. They range a little bit. All right, we just went to a table of I-beams. and we were looking at some of the shapes and things. I can't really broadcast stuff off the internet sometimes because I get tagged for copyright infringement sometimes, so I always have to be careful about that for those of you online, but you could have a look. Just Google I-beam table or something like that. You can see the different standard dimensions on I-beams. So the idea here is the W36 grouping of I-beams they're not all exactly 36 inches deep. They vary. We saw one that was 35 and 7/8. We saw another one that was about 36 and a half, et cetera, et cetera. Okay. All right, so let's calculate some moments of inertia so we know how to do that. So let's start off on page 720. So let's look at the basic definition. So the basic definition is an integral, which means to add stuff up of a distance from the neutral axis to an area squared times the area. And then you break that thing up into a bunch of areas, do that calculation, and add it up for all the different areas in the beam. All right, now the way I think about doing this would be to write a computer program. And let's find the moment of inertia of a standard rectangle that has a base B and a height h. So what I would do here is each time I do this, I need one discrete distance y, okay? So I can't use dx's for this because dx's would cut across the shape like that, and I don't have a single y distance. So if I need a y distance, I need to use a dy, okay? Which would just be a small rectangle running across the beam. The distance then from the x-axis to that dy would be essentially y. It's just how high it is. So I would write a little program that says, okay, go out there and sample, tell me how far you went, and that, tell the computer. The computer would tell me how far up you went to find that y. Now tell me what the area is. Now what the area is whatever dy is, which is that thickness you would select, times the width, which is the base. Okay. So I would set an increment on a computer program to do this. I'd sample up a distance y, and I would square that distance, and then I would multiply it by the base times whatever my dy increment is that I set. I would start running this thing at negative h over 2, and I would end running it at h over 2. That's how I would do that. Okay. So that's the process I would use. And I would just plug it into that integral and run it and see what I come up with. Okay. So we all right with those values? Okay. So the integral is y squared dA. I'm going to evaluate it from negative h over 2 to positive h over 2. The y squared is just y, because I'm going to measure up a distance of y to get to that little element. The area of the element is the base times dy. The base is a constant, so it can come out of the integral. So I'll be left with the integral of y squared dy. When I integrate that, I think that's y cubed over 3. I'll pull the 3 out because it's a constant, so I'll get b over 3, and I'll plug in the limits. It's h over 2 cubed minus negative h over 2 cubed. Those are the two limits. The cube of h over 2 is h cubed over 8. So I get b over 3 times h cubed over 8 minus a negative h cubed over 8. Okay, and minus the negative gets me plus h cubed over 8. So I get h cubed over 8 plus h cubed over 8, which is 2h cubed over 8 times b over 3. It's b over 3 times h cubed over 4, which is bh cubed over 12. So there you go. There's the moment of inertia of a rectangle about its own centroid. And that's a very well-known formula for a rectangle. And that's on the back of your formula sheet also. It's on the very bottom on the right there. There's some shapes. And bh cubed over 12 is the centroidal moment of inertia of a rectangle about its own base. Okay. So we good with that? Now that's kind of where we start with this. But what we end up doing normally, as we were just looking at, our shapes are not simple rectangles. We don't make most of our beams out of simple rectangles. We build things called I-beams and different other types of shapes that are composites of rectangles. So we need to have a way of calculating a moment of inertia about an axis other than the centroid. Okay, this is the centroidal moment of inertia, but moment of inertia will change depending on where your axis is, because that affects the measurement of y. So we need to have a way of handling that idea there, that we're not usually using the centroid of each of the rectangles. Okay. So let's see. Now, before we do that, though, let's just find the moment of inertia of a rectangle about its own base, okay? Now, again, as I was just mentioning, that's going to be a different number because the location of your axis influences how you calculate it. This is going to be a very similar process to what we just did. It's going to be the integral of y squared dA, but instead of going from negative h over 2 to h over 2, we're going to go from 0 on the base now to h, because we're taking the moment of inertia about this axis. Okay, so it's the same integral, y squared dA, which is y squared times the base times dy. It's just evaluated with different limits. So I can pull the b out, and I'll just integrate y squared dy. That's y cubed over 3, evaluated from 0 to h. I've got a base out in front, so that's base times h cubed over 3 minus 0 over 3, which is bh cubed over 3. I've just got a space to put that on 720 where we were just working. Okay. So you notice it's the same integral, but changing the limits very much alters the value of the integral, okay? So instead of bh cubed over 12, it's bh cubed over 3. It's 4 times as big, simply by moving the axis. Okay. Doing all right with that? Now, as I mentioned, a lot of these values for centroidal moments of inertia are kept in tables. And I've got a small table there on the bottom right of your formula sheet. Okay. Now, you can also use these tables to calculate I sub y also. Okay. So if we did this, if this is the base and that's the height, you could say that I sub x is bh cubed over 12. Now, what a lot of textbooks will tell you, if you look at them, is they'll tell you in their way of doing it that I sub y is then hb cubed over 12, right? The way I look at it is a little different. It's the same thing, but I just express it just slightly differently. What I do, I just define the base as parallel to the axis and the height as perpendicular to the axis. So what I would say is I sub y is also bh cubed over 12. Okay. Just two ways of expressing the same thing. I just changed the definition of base and height. I call the base parallel to whatever axis I'm using and the height perpendicular. And that way I can just use the same formulas. It's not a big deal. It's just however you want to write the formula. The idea is, the issue there. Okay. So it's whatever the dimension of a rectangle is that's parallel to your axis times the dimension that's perpendicular to it cubed over 12. Okay. Okay. Now, as I was saying, a lot of times you've got composite shapes. So if you have a T-beam like that, you're not going to take the moment of inertia about the centroidal axes of those rectangles. You've got two rectangles, and the axis you would calculate, which is the neutral axis, doesn't run through either of them. So you can't just use BH cubed over 12 for those rectangles. You have to compensate for the fact that the neutral axis of your total T-beam doesn't run through the centroid of either rectangle. So the way you do that is called the transfer axis theorem. And here it is. If you want to get the moment of inertia about an axis other than the centroidal axis, you take the centroidal moment of inertia, which for a rectangle is BH cubed over 12, and then you add the area of the shape times the offset distance between the two axes squared. Okay? So I about some axis is I bar about the centroidal axis, which is BH cubed over 12, plus AD squared. A is the area of the rectangle, D is the offset distance between the two axes. Now that formula will work for any type of shape. It doesn't have to be a rectangle. Okay? So you just take a centroidal moment of inertia plus AD squared, you get the moment of inertia about some axis. All right, now here's why this works. So I'm sorry, I got a little illustration of it over here. So here's some shape, here's the centroidal moment of inertia about the centroidal axis. If I want to find the moment of inertia about the red axis here, I would use I bar x plus AD1 squared. If I want to find the moment of inertia about the purple axis down there, I would use I bar x plus AD2 squared, okay? So I'm on page 732. Now the derivation for this is just a matter of plugging in the different offset distances into that formula there. So if I have I bar x is y squared dA, and if I offset to a new axis down below this shape here, down here let's say, and that offset distance is d, what the formula becomes then is integral of y plus d quantity squared dA. And if I use the FOIL process and expand that y plus d and square it, I get y squared plus 2 times d times y. Now that's not a calculus dy, that's a d times y. And then plus d squared dA, okay? The dA distributes between all three terms. So when I do that, I've got the integral of y squared dA for this term. Then I've got the integral of 2 times d, which is a constant, times the integral of y dA for the middle term. And then the last term, I've got d squared dA. The d squared's a constant, so it can come outside of the integral sign. So I get those three terms. Now the first one is y squared dA. Well, that's just the centroidal moment of inertia is all that is. So that just becomes I bar x. The last term is d squared dA. The integral of dA is just a, that's AD squared, that goes there. Now the middle term goes to 0 because I've got an integral of y dA for every positive y dA on the top, because this little calculation here is based simply on the y distances, which are measured from the centroidal axis. So for every y dA on the top, I've got a balancing y dA on the bottom, which would be negative. So that zeroes out. Being as you're at the centroidal axis, for every positive y dA you've got on the top, you've got a negative y dA on the bottom, so that zeroes out. So you're left with this expression right there. Okay. So that's the transfer axis term. It's used a lot when you find moments of inertia. So, we good with that? So, why don't we use the transfer axis theorem to find the moment of inertia of a rectangle about its own base. So let's go on down to, or go back to that page we were on. Page, 720. So what we're going to have is a rectangle. We've got the centroid of the rectangle. Okay, so I bar sub x is what? bh cubed over 12, right? Now we're going to take that axis and we're going to move it down here at the base, at the height. What's the offset distance between the neutral axis and the base? What's this distance right here? This is h over 2, right? So if we want to find I sub x for this x-axis down here, we're going to take I bar sub x plus ab squared. That's all we got to do. Now what d is h over 2, and I think what a is the base times the height. Okay. So we're going to take bh cubed over 12 plus ad squared. And a is base times height, and d is h over 2. So bh cubed over 12 plus bh times h over 2 squared is bh cubed over 12 plus bh cubed over 4. And then we got to go back and remember our fraction facts there. So what? bh cubed over 4, we need a least common denominator. Remember all that stuff? Go back that far with math. And we got to multiply top and bottom by 3. So bh cubed over 4 is 3bh cubed over 12. So bh cubed over 12 plus 3bh cubed over 12 is 4bh cubed over 12, which simplifies to bh cubed over 3. So that's the moment of inertia about its own base using the transfer axis theorem. What that is. Doing all right with that? Okay. Now we'll run through some examples Monday, I guess. Okay. So I'll go over the that test review. I could look at that on Monday. Okay. Is it good?